Look up at the night sky over the course of a month and you will notice a remarkable pattern. The moon changes shape. One night it appears as a thin crescent, another as a bright half-moon, and eventually as a full glowing disk. A few nights later it begins to shrink again until it disappears from view. This repeating sequence is called the lunar cycle, and it has fascinated humans for thousands of years. At the same time, oceans around the world are constantly rising and falling. Beaches that are covered by water at 1 hour may be exposed a few hours later. These changes are called tides. Although the sun plays an important role, the moon is the primary driver of Earth's tides. In this narrative we will explore two connected questions. How does the lunar cycle work? And why does the moon affect the tides? By the end, we will see how the motions of the Earth, Moon, and Sun create one of the most predictable natural rhythms on our planet. Part 1. The Earth-Moon System. To understand the lunar cycle, we first need to understand the relationship between Earth and the Moon. The Moon is Earth's natural satellite. It orbits our planet at an average distance of about 384,400 kilometers, or roughly 238,900 miles. The Moon completes one orbit around Earth in about 27.3 days. This period is called the sidereal month. However, Earth is also moving around the Sun. Because of that motion, the Moon must travel a little farther before it returns to the same position relative to the Sun. The time between one full moon and the next is about 29.5 days, known as the synodic month. This is the lunar cycle that we observe from Earth. One important fact is that the Moon is tidally locked with Earth. It rotates on its axis in the same amount of time that it takes to orbit Earth. As a result, the same side of the Moon always faces us. The far side remained unseen by humans until spacecraft photographed it in the 20th century. Part 2. Why the Moon changes shape. The Moon does not produce its own visible light. It reflects sunlight. At any moment, half of the Moon is illuminated by the Sun, while the other half is in darkness. As the Moon orbits Earth, we see different portions of its sunlit half. These changing views create the lunar phases. The new moon. The cycle begins with the new moon. During this phase, the Moon is positioned roughly between Earth and the Sun. The side facing Earth is mostly dark, so the Moon is difficult or impossible to see. Waxing crescent. As the Moon moves eastward in its orbit, a thin crescent becomes visible after sunset. This is the waxing crescent. Waxing means the illuminated portion is growing. First quarter. About a week after the new moon, we reach the first quarter. Half of the Moon's visible face is illuminated. The term quarter refers to the Moon being 1/4 of the way through its orbit, not to the amount of the disk that is lit. Waxing gibbous. The illuminated area continues to increase, producing the waxing gibbous phase. Gibbous means more than half illuminated. Full moon. About 2 weeks after the new moon, the Moon is on the opposite side of Earth from the Sun. We see nearly the entire sunlit face. This is the full moon. Waning phases. After the full moon, the illuminated portion begins to decrease. The phases are called waning gibbous, last quarter, and waning crescent until the cycle returns to a new moon. Part 3. The geometry of the lunar cycle. The key to the lunar cycle is geometry. Imagine Earth at the center, the Moon orbiting around it, and the Sun far away in one direction. The Moon is always half lit by the Sun. What changes is the angle between the Sun, Earth, and Moon. When the Moon is near the Sun in the sky, we see little of the illuminated half. When it is opposite the Sun, we see almost all of it. Intermediate angles produce the crescent and quarter phases. This is why the lunar cycle is completely predictable. Astronomers can calculate the phase of the Moon for any date in the past or future. Part 4. What causes tides? Now we turn to the oceans. A common misconception is that the moon simply pulls water toward itself. The real explanation is more subtle. Tides are caused by differences in gravitational pull across Earth. The moon's gravity is strongest on the side of Earth closest to the moon and weakest on the side farthest from it. This difference stretches Earth slightly, creating two bulges of ocean water. One bulge forms on the side facing the moon. The other forms on the opposite side. As Earth rotates, most coastlines pass through these bulges, producing two high tides and two low tides each day. Part 5. The role of inertia. Why is there a tidal bulge on the side farthest from the moon? The Earth and Moon orbit a common center of mass called the barycenter. As they move together, inertia tends to carry Earth's water outward. On the far side, this outward tendency slightly exceeds the moon's weaker gravitational pull, producing the second bulge. The result is a stretched Earth-ocean system with bulges on opposite sides. Part 6. Daily tides. A lunar day, the time between two successive moonrises, is about 24 hours and 50 minutes. Because of this, high tides occur roughly 50 minutes later each day. Many locations experience 2 high tides, 2 low tides. About 12 hours and 25 minutes between consecutive high tides. However, local geography can alter this pattern. Some places have only one significant high tide per day, while others have tides of unequal height. Part 7. How the lunar phases affect tides. The lunar cycle and the tides are closely connected. When the Sun, Earth, and Moon line up, their gravitational effects combine. This happens during the new moon and full moon. Spring tides. Highest tidal range. These unusually large tides are called spring tides. Spring tides produce higher high tides, lower low tides. The greatest tidal range. Note: the word spring here does not refer to the season. It comes from an older meaning of to leap up. When the moon is at first quarter or last quarter, the sun and moon pull at roughly right angles. Their effects partially cancel each other. Neap tides. Smallest tidal range. These smaller tides are called neap tides. Neap tides produce lower high tides, higher low tides. The smallest tidal range. Part 8. The monthly tidal rhythm. Because the moon completes a cycle every 29.5 days, the strength of the tides follows a monthly rhythm. New moon. Spring tide. First quarter. Neap tide. Full moon. Spring tide. Last quarter. Neap tide. This pattern repeats approximately every 2 weeks. Part 9. Why some tides are stronger than others. The moon's orbit is not perfectly circular. It is slightly elliptical. At perigee, the moon is closest to Earth. At apogee, it is farthest away. When a spring tide occurs near perigee, the tidal range can be especially large. These events are often called perigean spring tides. Conversely, spring tides near apogee are somewhat weaker. Part 10. The sun's contribution. Although the moon dominates, the sun also raises tides. The sun is vastly more massive than the moon, but it is much farther away. Tidal forces depend strongly on distance, so the moon's tidal effect is about twice as strong as the sun's. The sun's gravity modifies the lunar tides, creating the spring and neap patterns we observe. Part 11. Ocean basins and coastlines. If Earth were completely covered by a uniform ocean, tides would be relatively simple. In reality, continents, islands, and varying ocean depths complicate the picture. As tidal waves move through ocean basins, they can be reflected by coastlines, deflected by Earth's rotation, amplified in narrow bays, reduced in enclosed seas, This is why tidal ranges vary dramatically around the world. Bay of Fundy, Canada. One of the largest tidal ranges on Earth. 16 m plus Mediterranean Sea. Many areas. Much smaller tides in many locations. Less than 0.5 m Part 12. Earth's rotation and the Coriolis effect. Earth rotates once every 24 hours. This rotation causes moving water to be deflected by the Coriolis effect. In the northern hemisphere, water tends to be deflected to the right. In the southern hemisphere, it tends to be deflected to the left. The interaction between tidal forces, Earth's rotation, and ocean basin geometry creates complex tidal patterns called amphidromic systems, in which tides rotate around central points. Part 13. Historical understanding. Ancient civilizations noticed the connection between the moon and the tides long before modern physics existed. Greek philosophers, Arab scholars, and medieval astronomers all recognized a relationship between lunar phases and tidal strength. The first complete scientific explanation emerged with Isaac Newton in the 17th century. Newton's law of universal gravitation showed that every mass attracts every other mass, providing the theoretical foundation for understanding tides. Later scientists refined the theory by accounting for Earth's rotation, ocean dynamics, and the Sun's influence. Part 14. Tides beyond Earth. Tidal forces operate throughout the solar system. For example, Jupiter's moon Io experiences enormous tidal heating. Saturn's moon Enceladus has geysers partly driven by tidal flexing. Many moons become tidally locked, just as our moon is. Tides are therefore not unique to Earth, they are a fundamental consequence of gravity. Part 15. The moon is slowly moving away. Earth's tides do not only respond to the moon, they also affect the moon. Tidal friction in the ocean slows Earth's rotation slightly. As angular momentum is transferred to the moon gradually moves farther away from Earth. Measurements using laser reflectors placed on the moon show that it is receding by about 3.8 centimeters per year. Hundreds of millions of years ago, the moon was closer, and tides were stronger. Part 16. Practical importance of tides. Tides influence many aspects of human life. Navigation of ships. Fishing and aquaculture. Coastal engineering. Flood prediction. Tidal power generation. Beach and estuary ecosystems. Many coastal communities rely on accurate tidal forecasts every day. Part 17. Common misconceptions. Misconception 1. The moon pulls only on the ocean. In reality, the moon pulls on the entire Earth, including the solid planet. Misconception 2. There is only one high tide each day. Most locations experience two. Misconception 3. Full moons always produce the strongest tides. New moons produce spring tides as well. Misconception 4. The phases of the moon are caused by Earth's shadow. Lunar phases are caused by viewing geometry. Earth's shadow is involved only during a lunar eclipse. Part 18. Bringing it all together. We can now connect the lunar cycle and the tides into a single picture. The moon orbits Earth every 29.5 days relative to the Sun. As it moves, we see different portions of its sunlit half, producing the familiar sequence of lunar phases. At the same time, the moon's gravity creates tidal bulges in Earth's oceans. As Earth rotates through these bulges, coastlines experience rising and falling water levels. When the Sun, Earth, and Moon align during the new moon and full moon, spring tides occur. When the moon is at first quarter or last quarter, neap tides occur. The monthly rhythm of the tides is therefore directly linked to the monthly rhythm of the lunar phases. Conclusion. The changing face of the moon and the rise and fall of the oceans are not separate phenomena. They are two visible consequences of the same celestial dance. The lunar cycle is produced by the moon's orbit around Earth and the changing angle between the sun, Earth, and moon. The tides are produced by the moon's gravitational pull, modified by the sun and shaped by Earth's rotation and ocean basins. For thousands of years, people watched the moon and the sea without fully understanding their connection. Today, through astronomy and physics, we can explain both with remarkable precision. Every crescent moon, every full moon, every high tide, and every low tide is part of a predictable pattern written in the motions of the Earth-Monson system. The next time you stand on a beach at low tide or look up at a bright full moon, you are witnessing the same gravitational relationship acting across nearly 400,000 kilometers of space, a relationship that has shaped our planet's oceans, calendars, ecosystems, and human history for countless generations.